Okay, thank you. Welcome, Power System Operation and Control course. In today lecture 5, we will discuss economic disperse and optimal power flow topics. What is economic disperse? Economic disperse means least cost generation selection to meet the demand. Here we see, for example, 3 generator A, B, C connected with common bus with load L. So I have to serve this load by using these 3 generators. Generators are defined by their cost function actually and their limit. So the least cost generation would be select first, and then the second one, and then the third one. In this way, we have to fulfill the demand. So objective function is nothing but cost minimization. We can see in this way. A minimum if J function of P generation. J is the index for generation and N generator is the total number of generator in the system. So we have to minimize the cost. This is the first objective. But there are certain constraints we have to fulfill. As we mentioned, the supply must be equal to total demand, the total demand plus total loss from all the generators. And then this is actually the one constraint. And there is another constraint. This constraint is called global constraint. And there is another constraint. It is actually inequality constraint. Its generator is within its minimum and maximum limits. So this is the lower limit of a generator J, and this is the upper limit. So for all generators, we have to maintain their limit. This is the basic formulation. Economic disperse we already discussed in course optimal power system optimization 6404 course actually. So we formulated a detailed model. Also, we covered these topics in this courses as well. But our target is to discuss the optimal power flow model. So before discussing the optimal power flow, we'll discuss some limitation, why we consider OPF rather than optimal power flow. So limitation of economic disperse, one of the limitation is, as we consider that load and generators are connected in common bus, but practically it is not feasible. Usually generators are placed, the plants are placed where the resources, fuel resource is available or the power supply resource is available. For example, in hydropower plant, usually set where the water head is enough. In Bangladesh, like Kaptai area, Kaptai power plant, in that vicinity, there are huge water head in the rainy season. You know that. And also in other countries, like Nepal, use water come from the mountain, and they dammed it and preserve it. Then they allow the turbine to rotate, and they use this rotation or this kinetic energy to rotate the turbine of the generators, blade of the generators. In this way, they convert the power. So that area, we know that the power source usually in where the fuel is available, but the loads actually distributed. But this economic disperse used only for analysis which fuel is have to choose for cost effectiveness. That is why we consider economic disperse to get a rough idea. But definitely we have to consider network, detailed network, how the loads point or connecting with point of common coupling, or the all the load aggregated and connected in a the grid substation like. So we have to consider detailed model, also the transmission line capacity limit, resistance and reactance of the line. So these things have to be considered in the model. So economic disperse have some sort of limitation like this. Sometimes the results from the economic disperse we cannot rely. It is unacceptable in the point of flow in the networks. Example of network limitation like maximum, we see in this figure, double circuit transmission line connecting generator 1 as generator A and generator B. The load LA in this bus where the generator A is situated, and in bus 2 or bus B, we can say that this is the bus B where the generator B is located. So here is the load is LB. So maximum flow on each line is 100 megawatt. The cost function for generator A is shown in the bottom of the left corner. The per megawatt hour generation cost from this generator is $50 like. And the maximum limit of this generator A is PA max. Certainly there is a limitation of the maximum power it can provide it or supply. And similarly, the generator B cost curve is like shown here on the bottom right corner. Its fuel cost is $100 per megawatt hour. For each hour, if it produces 100, how much it produces, but for each megawatt, it have cost $100. So it's also has a maximum limit. So in this case, if we consider the real some value in it, like load, the generator A bus has 100 megawatt, and LB load, that is bus in B bus has a 200 megawatt load. So altogether 300 300 megawatt load. It have to be supplied by using both of the generators. But which generator have to we choose based on economic point of view? Definitely generator 1, if it's didn't cross the maximum limit. The solution of this trivial economic disperse is that is P is going to produce 300 megawatt. PV is not producing anything. So serving the local 100 megawatt, the rest of the 200 megawatt will supply to load P. And as we said that its maximum limit is 100 megawatt, so it can easily flow through the transmission line. Okay, the flow on the lines are below the limit. The economic disperse solution in particular this case is acceptable. When it will be an unacceptable solution? If load increases, we know that that is the operation level model. So load will not always be constant. It will changes. Peak hour may change 50% or 30%. it depends on the devices or load duration curve in particular area. So if load increases, then for example 500 loads 100 megawatt in this bus A, and 400 megawatt load in in this bus. So the solution of the economic disperse, if this limit within the limit, then it will be 500 megawatt. So 500 megawatt after supplying 100 megawatt load in this bus, then 400 megawatt load will flow through, power will flow through this transmission line, and this actually violates the limit, exceeding their maximum power transfer limit. We said that 100 megawatt is maximum limit of this transmission line. So this solution is unacceptable. Economic disperse solution is not. Economically it is okay, but if you consider the transmission line, it is not acceptable. So we have to modify the solution. We have to modify the solution. We consider that it will not totally produce the 300 megawatt. We have to give limit here, so that rest of the supply power will be supplied from the generator B. So if it is produced 300 megawatt rather than 500 megawatt, then after supplying 100 megawatt, the rest of 200 megawatt will be equally distributed through this double circuit line, and 200 megawatt from this generator and 200 megawatt from this generator. Total will be supplied, and together 400 megawatt load. So we have to correct or modify in this way. In this simple case, the solution of the economic disperse can be modified easily to produce acceptable flows. This could be done mathematically by adding the following inequality constant, like the generation from PA, from generator A, minus the load amount, this local load should be less than or equal to 200 megawatt. However, adding inequality constant in this way for each problem is not practical in more complex situation when hundreds of generators are in the system, huge amount of loads distributed throughout the network. So in this case, we have to find a general approach. We have to find a general approach, and that is the optimal power flow model comes for. So if we summarize the limitation of economic disperse, the ED finds the lowest cost generation definitely disperse for a set of generator that is constant within the individual generator limits. Total generation that equals the total load plus losses. The loss here considered as lumped, incremental loss of the generation capacity of a particular generation plant. We have considered incremental loss, not like distributed loss as the realistic transmission line consider. The ED calculation ignored the specific details of the network, definitely, that the generators are connected to, lumps all the network effects into the losses and the total loads demand. The ED calculation ignored the effect that the disperse of generation has on loading of transmission branches, or the effect it has on bus voltage. Another thing is that we will consider the bus voltage in particular this case is unity, but practically not. The bus voltage change and should regulate it within the certain limits by using voltage regulator. So in this case, economic disperse problem, we consider for each point the bus voltage is same 1 per unit. So the disperse of generation does in fact have an important effect on transmission flow, definitely, and under some circumstances this effect need to be taken into account. And here the optimal power flow come. to solve this or solve this limitation, to overcome this limitation. The optimal power flow, as the name implies, couples the ED calculation with power flow calculation. So here also we consider economic disperse, means the generation cost for all generators in the system should be minimal as possible. And we simultaneously will consider the power flow through the networks, how the loads are connected through the networks with the generation source. So these have to be taken care in OPF. The total loss of the power system is simply parts of the power flow calculation. We in economic disperse, simply we consider incremental loss, that is how much it produce, what is the percentage loss may become. So we consider a rough figure or lumped figure, but here as we consider the detailed model of the power flow model, power flow using power flow equations, so definitely we can taken care of the loss, and which reflected the loading of the generation. Thus, there is no need to specifically calculate the losses since they are inherently a part of power flow. More importantly, the ED can be constant to meet transmission system limit. ED, that is a ED here within the optimal power flow model. So in this case, we can say constant transmission line capacity constant ED maintain the limits of the transmission line, maybe in megawatt or megavolt ampere. Further, the ED can constant transformer loading or voltage limit on bus. We will not consider constant voltage. We will consider realistic voltage value which must be regulated within a prescribed limits. The result is the generation disperse representing the minimum dollar here per hour or BDT per hour total generation cost. Also maintain here minimum cost and also serve the power flow at that optimum or power flow through the network. So here I'll discuss which is contained in this slide. Then I will move to the book, LNG Wood book. So I'm stopping here and sharing the new file from the book. So this chapter 8, optimal power flow. In this chapter 8, the ELD or ED problem formulation still have this ELD problem already formulated in chapter 3 also. We already discussed these things in our earlier semester, the last semester, even odd semester. But ED problem we will discuss for this semester from chapter 8. So what we discuss in the slides, these contents are repeated here also in chapter 3 of this book. Here this formulation, objective function, then local generator constraint, and the load and loss is equal to the generation from all the generators. So here we indexing J as number of generators. There is no consideration of network. So we'll read or we'll consider this formulation from the book, from this chapter actually. Here we P gen means a generation amount from a particular generator from 1 to up to nj number of generators. So it is a vector like, and new variable appear here u. It is called control variable. How much generation as it is a operation power system operation and control. So if economic disperse things actually run every hour or for day ahead uh, scheduling. So we have considered the 24 hours load. So what is the difference between 1 hour average power and for the next hour? So there is a some control action taken care to adjust the prime mover input. So there are some control variable initialized here u, but actually control variable implement to adjust the power. So actually the power Pgen is the output, but we can simultaneously consider the variable u as well. Anyway, so objective function is this, and two constraint. One is omega. Omega is equal to supply equality constant. Supply is plus demand equal supply minus demand equal to 0, or total loss load plus loss equal to generation, we can say. And the another is the inequality constant G. G uh, uh, that is the limit of the generators. If there are 10 generators in the system, then the number of equation will be how much? 20. We will break this equation in two way. Two equation we have to. There are two equation in this expression. So in this way, we can, if we solve this problem, we can find the generation amount from each generator. We can calculate it, maintain it so that the cost is minimum. So we can solve this. What is the procedure of solving? We already know in the last course, last year, last semester course, like Lagrangian method. Lagrangian method. So that detailed treatment are still in chapter 3, how the Lagrangian function produces, considering these three equations, like uh, summation of the objective function, sorry, or summation of the two equations, constraint the multiplier, multiplying the constraint or multipliers with the constraint, plus the objective function makes the Lagrangian function. And then we differentiate this Lagrangian function with respect to its variables, and this produces a set of equation, algebraic equation. After solving this algebraic equation, we will find the generation amount, optimal amount, and also the price, how much amount have to sell or purchase with which price. So these variables, auxiliary variables come. We already discussed these things. I think if you need any review, revisit chapter 3 for detailed treatment of Lagrangian method. So I'm stopping ELD here, and we will go for OPF. OPF, optimal power flow calculation, combining economic disperse and the power flow. So in OPF calculation, we solve the following more complex problem. What is the complex? Complexity arises due to network. So objective function similar. ET problem has objective function, cost function of the generators based on fuel source. Cost function is actually polynomial cost function having second order polynomial function, that is fuel cost increases with the capacity, the generation for particular generator supplied. This type of second order equation will be the cost function. Similar cost function will be here also. If we consider second order function, then the problem will be non-linear. But if we consider just slope of the generation cost, that is differentiation of the cost function with respect to generation amount, that will make a tangent of the second order function, which serve as a marginal cost of the generators. not the system cost, generator cost. So this, if we consider, if we make the optimal power flow linearized, then we have to manipulate the cost function and make the cost functions linearized by differentiating just one time at once with respect to the generation. Anyway, generation limit inequality constant. Generation limit is still OPF have, but the change or modification is the network. Network the generation supply and demand constraint have to maintain or have to meet in each node of the network, like KCL. So generation minus load at bus, the equal to the need power flow at the bus. If we consider, for example, a bus or a node, there are two generators and one load, the same node connected with two transmission line with other two buses. Then how will be the case here? That is injecting power from two generators. Outgoing power is actually two transmission line and one local load. So in this way, this KCL, like incoming current, is equal to outgoing current. So in this case, for all the buses of the network, in the transmission case, in the transmission line, all the networks, all the nodes actually maintain in this way. So we can say generation minus load at bus is generation minus load at bus equal to the need power flow at the bus. So we can say it in this way. Let me read out loud. So this is one of the things. Then this is done using the Y matrix power flow equation for the bus. Y matrix, we need Y matrix, that is impedance inverse of impedance matrix. We have to manipulate the component of the matrix will be the resistance and reactance, how the line are connected with particular node. This type of stuff need to be revisited to get idea about Y matrix. I think you all know what is Y matrix. So Y matrix need to be here to figure out the network. And why this introduce the voltage magnitude and phase angle of each bus. We have to know the voltage magnitude and phase angle, except for reference bus. Reference bus, we can consider the voltage magnitude is 1 and angle is 0. So except that, this is 2n-1, the new equality constant into the problem. And why 2 times? Because both are real power and reactive power. So real and reactive power constraints are considered. So in this way, we have this type of inequality constraint, equality constraint in the system. This, and the notion is changed slightly OPF than the ED. Variable P gen I is the generation on bus I. Previously, we only considered the J index for the generation generation number or plant number, power plant number, which number power plant is. So we indicated by J, but in this case, we will consider I. I is not number of particular number of generator, I is the bus number. So from now on, this chapter will always refer to the generator as being at a specific bus and not by generator number. The OPF equation now look like this. Still, we have to minimize the cost function, and for all generators indexing from I to N bus, those bus having generators, and I is the index over buses and Fi, Gp, Gn, I is the cost function of the generator at bus I. Generally, limit inequality constant, like previous, we will indicate here J, and we will indicate in this case or OPF Ji. I is index for bus for all I in the network up to n bus having generators. Generator var limit. Var limits mean reactive power. There is some reactive power generation limit for each of the generators. So this is the generation reactive power generation limit. Power flow Y matrix equation for each bus I. This is a power flow. Power flow in the network. Need power, real and reactive, is equal to voltage and current. This is actually produce current flowing in the network. So this transpose the star indicate the transpose. So if we complex this is complex power current. So if we consider this multiplication of this and these terms, this will the apparent power. So apparent power is like nothing but real and reactive power. So there are set of Y matrix here, YIK, the elements of the matrix. So here P net and Q net are the net real and reactive power at bus I. Vi is the complex voltage at bus I, and YIK is the Y matrix, IK in terms. For OPF, the net real and reactive power are replaced with the generation minus the load. So that we have definitely in the network, we have load, real load and reactive load, reactive power actually tapping out from the line. So we have to balance generation minus load plus need power actually is equal to this term. So if we separate the real and reactive, real and imaginary part from this this side expression, then we will say real power this way and reactive power in this way. So as indicated earlier, the fact that we are solving the power flow itself result in a set of generator output that equals load plus loss as required. So here we will not have any separate loss equation, but loss are still there because Y matrix are here. Y matrix have the elements of R and X. So loss are here distributed throughout the transmission line, not lumped. So we are loss are taken care of. We do not have explicitly calculate the loss or generate incremental loss as they are also incorporated in the AC power flow equation. So in this way, we formulate the details network and flow in the system. We can again use compact notion of the objective function like minimum cost function, control variable still here u, generation, and subject to equality constant. Equality constant has two components: real power equality constant and reactive power equality constant. And then this term is for inequality constant. Inequality constant means the limit of the generation. Also the voltage limit. Also the voltage limit. Voltage we will consider not unit voltage in each bus. We are considering limit of the voltage. For example, lower limit 0.95 per unit to 1.1 or 1.15 maximum. These are the limits of the voltage. Further, the transmission line and maximum limit, that is also an equality constant. All these constants are here. So these are a few more inequality constant come. earlier in OPA economic disperse problem, we only considered the generation lower limit or upper limit, but we will additionally we are considering the transmission line maximum limit plus voltage limit. So in this way, we are considering this inequality in this form, in shortest form. So this is the short form. The previous expression, if we manipulate, or then this is the maximum flow limit, the real power limit expression, then maximum limit shouldn't cross. This way we can write, and the voltage limit I already mentioned. So this is the OPF general formulation of the OPF, having considering the network with the voltage limit and the transmission line limit, and we have to get the optimal value of the generation from each of the generator. What is the value of the power it produces, the selling price, like, and what is the uh, the, uh, the retailer, like, they are purchase how much amount and what the price is. All are still can be calculated after maintaining the procedure or methodology of the solving this problem. How we solve, we will discuss in the next class, considering Lagrangian function or Lagrangian method. So this are the content for this class. In the next class, I will discuss the process of solving